So there are three basic types or forms of FIR filters. I'm trying to avoid the word types because the word type is reserved for FIR filters in a different context, which we will study after this lecture. So the three basic forms are, one is you fundamentally work with low pass FIR filters with, let's say that your omega C is the cutoff frequency. Okay. Now, a low pass FIR filter, if you have the omega C as the cutoff frequency, one key aspect is if you look at the pole zero diagram of that FIR filter, and let's say omega Z, if it's low pass, of course, you are saying your cutoff frequency is less than pi. Let's say this is your cutoff frequency, maybe pi by 4. So this is your cutoff frequency, omega C, which is just the angle that you make with the x-axis. Now, if this is your pole zero diagram of your FIR filter and your omega C is your cutoff frequency, then for a low pass filter we know that we better not have any attenuation in this region. Okay. So we don't want any attenuation in this region, which means that all the zeros of your filter are away from this region. For example, we last looked at a moving average filter of order 4, which is effectively a low pass filter. Its zeros are here, here, and here. Right? So you can have zeros anywhere away from the omega C region, but a low pass FIR filter will have zeros that do not lie in this region, which is spanned from minus omega C to omega C. Okay, so this is an example of a low pass filter that I designed using what is called the Frequency Design and Analysis tool, or FDA tool. And this is an order 10 low pass filter, and the cutoff frequency for this was set to be about 0.1 omega C. And as you can see that you don't have any, of course, zeros in this region where you are trying to be low pass. Now I could actually modify the locations of these zeros, right? And as you see, as I bring them closer and closer to 0, your cutoff frequency is going back and back, right? It's getting smaller and smaller because now you are really attenuating the frequencies near 0. So I better make sure that all of my zeros are away from my cutoff frequency. Okay? So that's basically the principle, that if you see a picture like this, you can infer without even doing any formal analysis that it has to be a low pass filter because there is all this region around 0. There is this arc around 0 which has no zeros in it. Okay. Now we can talk about the high pass FIR filter. With again omega C cutoff frequency. And using the same intuition, we can say, so a high pass FIR filter, if it has cutoff frequency omega C, of course that means that you want to avoid any attenuation near pi of that cutoff frequency. So let's say your cutoff frequency is, this is your omega C, and this is your minus omega C. Now, for a high pass filter, you don't want any attenuation in this region, in this arc. Right? So, this is the arc where you don't want any attenuation. And all the zeros should be away from this arc. If you think of it, this is just a mirror reflection of what a low-pass FIR filter will look like. In general, you can have zeros anywhere in this region away from this main arc. Right? So this is your pi frequency, and you want to be non-zero, or you want to have less attenuation around pi. So just looking at this diagram, a high-pass FIR filter is simply equivalent to a low-pass FIR filter with all the zeros shifted by pi radians. In other words, if I give you a high pass, if I give you a low pass FIR filter, for example, or high pass, getting the other FIR filter, given a low pass FIR filter, designing a high pass FIR filter is trivial. Right? How you just take that and place its zeros at a shifted by pi radians. Right? So if your low pass, if the low pass filter has zeros at the k equals to r to the k e to the j phi k, right, then you get a high pass FIR filter by simply placing the zeros that are shifted by e to the j phi k plus pi. And of course, a shift by pi is simply equal to minus rk e to the j phi k. Okay. So, in other words, if the z transform of the transfer function of your low pass filter is given by, it's an order m filter, so it's k equal to 1 to m, z minus zeta k. Okay. So it has these m zeros. Then from this you can get the transfer function of your high pass filter by simply replacing z by minus z. Okay. You replace z by minus z because this is equivalent to saying that you are just multiplying it with a negative sign. A shift by pi is simply multiplying with a negative sign, so that will be p naught pi k equal to 1 to m minus z minus zeta k. Okay. So a high pass filter gives you a low pass filter, and similarly a low pass filter gives you a high pass filter through the simple shift of your zero. So this is a low pass filter with just 3 zeros, right? This is just a moving average filter. It has order 3. Now, if I just, so this right now is a low pass filter because it doesn't have any zeros in around 0. Now, if I just shift this 0 to the other location, right? Now its behavior has changed. It is actually around 0. Of course, it's having a strong dip. Let me place it better. And around pi, it is not attenuating the frequencies anymore. So I just did a shift. Of course, the other 2 zeros, when I shift them by pi, they just interchange their position. So nothing changes. But this is the 0 that changes, and just by flipping all the zeros, I go from a low pass filter to a high pass filter. Another basic form of FIR filter, which we briefly talked about last time, is what's called an FIR notch filter. So a notch filter is basically a filter that kills off just one frequency. So sometimes we are interested in killing or severely attenuating just one frequency. Let's call that frequency omega naught radians. And the filter which does that is called a notch filter. Okay. Now, since we are talking about real valued filters, when I say omega naught frequency, it also attenuates minus omega naught frequency. Okay. And the classical example of this is if you have some electronics which is operating near a power line, then you get an interference in your signal which is proportional to the power line frequency, 50 hertz or 60 hertz, depending upon which country you are in. And what you want is just remove that power line frequency. So, for example, if you are 50 hertz power line, then you want to design a filter. First of all, you figure out what is your sampling time, and based upon that, you convert that 50 hertz to a discrete frequency, and then you find out whatever is the value omega naught minus omega naught. You want a filter which kills the frequency omega naught, but does not attenuate the other frequencies that much. A notch filter which goes to zero around omega naught as sharply as possible is a better notch filter. But in general, designing a notch filter, a basic notch filter, is very simple, because we know that a notch filter means that you want your omega naught frequency to be killed, which means that you want your magnitude response at omega naught and minus omega naught to be equal to 0. Now, if you want your magnitude response at omega naught and minus omega naught to be 0, in terms of Z transform, in terms of the transfer function, what are we asking for? So if we want to design a notch filter with a cutoff, with the notch being, so if the notch is at plus minus omega naught, this means that we want a 0. We want a 0 exactly on the unit circle so that the frequency goes to 0. So we want a 0 at e to the j omega naught and at e to the minus j omega naught. So if the notch is, for example, at pi by 4, you want a 0 at e to the j pi by 4 and e to the minus j pi by 4. Okay. So a notch filter a typical notch filter, or the simplest notch filter, is one which has a 0 on the unit circle. This is the location e to the j omega naught, and it has a 0 at e to the minus j omega naught. Okay, and you say it's a notch filter with a notch at omega naught frequency. Now, so what will the filter look like in the time domain? What's the impulse response of this filter? Well, evaluating that is simple, because you start with the Z transform. So if you are given two zeros, you know that the transfer function of this notch filter is simply, it has a 0 at e to the j omega naught, so it's e to the j omega naught z inverse, right? That is one factor, and then it has a 0 at e to the minus j omega naught, so that's 1 minus e to the minus j omega naught z inverse, right? So these are the two zeros, you multiply them, you find out the final transfer function, it will be 1 minus e to the minus j omega naught z inverse minus e to the minus j omega naught z inverse plus z to the minus 2. Okay. So this will be equal to 1 minus, now I just take z inverse common, it's e to the j omega naught plus e to the minus j omega naught over 2. Okay. I'm just trying to write it more nicely, so this is what I get. Now using the Euler's identity, that is 1 minus 2 z inverse, that's cosine of omega naught plus z to the minus 2. So this is your transfer function, and from that we can compute the impulse response. So we know the relationship between the impulse response and the transfer function, which is that we can just read the values of the coefficients and they correspond to the impulse response value. So this is positive power, not negative. So we can just read off the values of the impulse response, and this is then h of 0 is 1, h of 1 is minus 2 cosine of omega naught, and h of 2 is z is 1. So this is n equal to 0, this is n equal to 1, and n equal to 2. So effectively the impulse response, what this is saying is that the simplest notch filter has an impulse response. It has n equal to 0, it is 1, and at n equal to 2, it is 1 also. And n equal to 1, the value at n equal to 1 is determined by where you want the notch to be. It is minus 2 cosine of omega naught. So wherever you want the notch to be, based upon that, this is what will determine the location of your notch. Okay. For example, if someone said that h of 1 is equal to, let's say, 0.5, well, from this you can calculate where the notch will be. Right? So this means that this means you are saying minus 2 cosine of omega naught equal to 0.5. And so cosine of omega naught is minus 0.25. And then you just simply take the cosine inverse. So omega naught is r cosine of minus 0.25. Okay? And you figure out where your notch will be. So this is a notch filter which we built by simply having the first coefficient is 1, the third is 1, and the second we picked omega naught to be pi by 4. So indeed, if we see the notch, it has a notch at 0.25 radians. Okay? And if you look at its pole zero diagram, you see that it has a 0 at omega naught and minus omega naught. Okay? If I change my omega naught to, let's say, pi by 6, I calculate my b again. Now it's a different value. I set h of 2 to be b. I do FV tool, and indeed it's, so now I'm doing pi by 6, and my value has moved on. The notch has moved on to the value of pi by 6. Right? So very simple to build a simple notch filter. It's trivial, just a length 3 filter. Now, one thing you should be careful about is that depending upon where the notch is for this simple filter, so if your notch is less than, so if omega naught is between 0 and pi by 2, okay, then your notch filter will look like this. Its magnitude response will look like this, which means that there will be some attenuation in the region around omega naught. And the reason is because you have two zeros which are close to each other around the omega equal to 0 frequency. On the other hand, if the notch filter is in the range pi by 2 to pi, then you will have the opposite effect, that you will have more attenuation around the pi region and less attenuation around the 0 region. So this is supposed to be symmetric around 0. So this is minus omega naught. Pi by 2 is somewhere here. Minus pi by 2, pi by 2, and this is omega naught. Okay. And the reason is because now you have your zeros are, so if you think of it, your zeros are now in this region. So because the two zeros are close to each other in this area, you have a little bit attenuation for frequencies between these two zeros. Okay. You will still have the notch at exactly the omega naught location, but whether the frequencies really get pulled down for other values of omega is a function of where your notch is located. Okay. So these are three basic types of FIR filters. Of course, you can have an FIR filter which is neither a low pass or a high pass or a notch filter, and then designing FIR filters in that case, if you want to use pole zero diagrams, the only thing you have is the location of zeros, and what you can do is move the zeros around. For example, just open MATLAB and place zeros at different locations till you are satisfied with the frequency response that you are looking at. And then you simply write down your impulse response using that transfer function. Okay. So it's a little bit of an art involved in that if you want to follow that procedure, because what happens is that once you start adding more and more zeros, sometimes unexpected things can happen because the different zeros start interacting with each other. But for a small order filter, having a few zeros, it's very easy to figure out what will be happening to the frequency response as you move your zeros around.